Hate TCP/IP.
That's true. Welcome to technical session number 19. We're going to be getting into TCP/IP. Talking about some of the network protocols that we use on a regular basis. We're going to be getting into the OSI models and the DoD model, which is going to be slightly different than the Google model you've been learning on Coursera. So we're going to be talking about those a little bit as well. We're going to be getting into some of the characteristics and properties of the TCP/IP infrastructure. And I know y'all have been waiting. We're going to start talking about TCP and UDP ports, protocols, and their purposes. BSMs we want to keep in mind for this particular one is adaptability. Got a lot of information being thrown at us at this point in time. Whole lot of acronyms, whole lot of protocols, whole lot of information all at once. And we have to try to adapt and overcome for the most part. But also want to keep in mind personal responsibility. Holding ourselves accountable. Making sure we do the things we say we're going to do. We're keeping up with the work as we move through this. And it extends, beyond this course, but also keep in mind, personal responsibility is taking responsibility for the good things you do as well, especially in the job world, because you need to be your best advocate and cheerleader. Doesn't mean you need to, be singing your praises all the time and how wonderful and awesome you are, but especially around the time of reviews and bonuses, you need to be talking about all the things you did well. You need to have specific examples. You need to use quantifiable measurements so that you can basically express to your boss how good of an employee you are. So you take responsibility for the bad, but also the good. All right, quick overview of TCP/IP. Yuki, can you please read for us?
Yes. TCP/IP overview. What is a protocol? A set of rules that are agreed upon when communicating electronically. What is TCP/IP? Transmission Control Protocol. Internet protocol is a collection of protocols used to communicate over most modern networks, including the internet. What is a host? Any machine or interface that participates in a TCP/IP network, whether as a client or a server.
Excellent. Thank you, Yuki. So protocol, set of rules. Everybody agrees how they function. TCP/IP, it is a collection of these rules over the internet. It's one of the most common ways that we communicate over the internet. And it's kind of a way where when computer A is talking to computer B, it's basically setting the standard, what I want to talk about and how we're going to communicate. So when I'm linking up with, DW's computer, I can tell it I'm looking for email. And I would use one of the 3 protocols where if I'm sending him email, I would be sending it to, out through port 25, but he would be receiving it. So he would receive it under, 110, or what was the other one? 125? No, 125. SIMAP 143. Anybody?
Yeah, if it's unsecure, yeah.
So 143 or 110?
143.
I need more caffeine. Do what?
143 for IMAP.
143, there we go. I got hung up on the 10s. So a host is essentially any machine, whether it's a client or server, in general. So we just kind of talked about this a second ago. Protocol is a set of rules and it governs how the communication is going to take place. And then a suite of protocols is just a group of those same bundled together. And then the most common one or most popular one at the moment is the TCP/IP protocol, not necessarily because it is superior, but because the majority of the internet utilizes it. It's one of those like not, you know, it's not the most advanced technology that wins, it's the most adopted. Betamax and VHS. HD DVD versus Blu-ray. Not necessarily superior technology, but which one is adopted the most? So some other ones that, you know, have gone the way of the legacy is the Apple Talk and IPX, SPX, NetBIOS, and NetBEUI. So these are essentially legacy network protocols. So we want to talk a little bit about protocol layers, how they operate. You've seen the 5-layer Google model. This is the 4-layer DoD or Department of Defense model. So they combine the physical and the data networks together in one, calling it the network access layer. And this would be your physical cables, it would be your point-to-point protocols, your frame relays, and then your Ethernet protocols to speak over the network. They took the network layer and they changed the name of it to the internet layer. And that's where your IP protocols are going to be, your IP version 4, IP version 6, things like that on layer 3. Remember I was talking about routers being a layer 3 protocol? Well, on layer 3, they deal with IPs. So that is why they call it a layer 3 protocol. Transport layer is the same in both the OSI, the DoD, and the Google. And that is where it determines whether it's going to be a TCP or UDP protocols. We will be talking about these a little bit more in depth as we go along. And then your application layer is the combination of the top 3 layers, much like the Google 5-layer model does this exact same thing. And they also call it the application layer. But of the OSI layers, the 7-layer model, they combine the top 3 to create a single model or a single layer. Do you need to be overly familiar with this? Kind of. You need to know what layers of the 7-layer make up the 4-layer. So like you need to be able to cross the 2 over and understand what layers of the 7 are combined to make the 4-layer DoD model. They have a pretty good graphic on this in the Cybex book. I'll see if I can find out what page it's on where it directly lines them up side by side so you can see what layers are combined together. Questions so far? This is a 4-layer DoD or Department of Defense model. All right. So layers of communication, this is kind of how it works, where you have the user interacting with the computer, essentially wanting to send data or retrieve data from another source. It sends this information down through the layers until it gets to your network card, which the network card will turn that into 1s and 0s, where it gets kicked out over the internet. When it gets received by the other network card, it takes those 1s and 0s and starts recombining that network frame and then sending it up through the layers until it gets to the other host it's wanting to speak with and interacts with those protocols. And if it's trying to retrieve data, that information will package it back up, send it back down until it gets to the network card, turns back into 1s and 0s, sent across the internet, and then back up through the layers. I do have a video that breaks this down pretty good. Mike Myers does a really good job of it. I will show that video for you guys a little bit later today, and it kind of shows you how the protocols are built on top of each other and then breaks it back down so that the system can use the information. It's a really, really good visual representation, though a little quirky, but it helps stick in your mind. So, questions so far? All right. Danielle, can you please read to us about application protocol?
Application protocol, hypertext transfer protocol, HTTP, is a protocol that governs the way a web server and a web client interacts. HTTP defines the content and formatting of the requests in response that are exchanged between the client and the server.
Excellent. Real fancy way of saying this is how we interact with the web server. So you have the HTTP protocols that governs how we would communicate with the web address. If we're going to Google, if we're going to our internet mail or Outlook or what have you, when we're looking at web servers and we're trying to get this information, HTTP protocols will govern this. Then we're going to get to break it down just a little bit more. JR, can you please read about transport protocols?
Transport protocol. Transmission control protocol is the transport protocol that manages the individual conversations between web servers and web clients. TCP divides the HTTP messages into smaller pieces called segments. These segments are sent between the web server and client processes running at the destination host.
Excellent. Thank you. So sometimes we're requesting chunks of data that are so big that we can't just send it all in one piece, because if we tried to, it would, much higher likelihood that it would error out, it would take a lot longer, all that kind of fun stuff. So it breaks it down into much smaller, manageable chunks. And it sends that information out to the internet, and they may go different routes to get to the final destination. When they get to the final destination, it's reassembled almost like a puzzle before you actually see that information presented on your screen. And the nice thing about transmission control protocol, or TCP, it actually verifies this information. So it creates a through a handshake when it's initiating a conversation, basically saying, hey, I'm about to send data. And you're like, okay, yeah, I'm ready to receive it. Okay, sending data. And as it sends the data over the course of this conversation, it's going to be checking and verifying that the data it's sending is being received. And the data that's being sent is numbered, one, so that they know where in the puzzle it goes and how much information it's expected to receive. And so if it doesn't receive everything, it can request that data be sent again. All right, Bernard, can you please read for us on internet protocols? If you're reading, you're muted.
You just asked Greg? You said Greg?
Nope, said Bernard.
All
There he
right.
is.
Okay.
Got you now.
Internet protocol. IP is responsible for taking the formatted segments from the TCP.
And this one got me for a while. Encapsulating. It's like closing around it.
Encapsulating them in packets, assigning them to the appropriate address, and delivering them across the best path to the destination host.
Excellent. Thank you, Bernard. So the internet protocol basically just breaks it down, formats them so they can go over the internet, and then making sure it's going where it's supposed to go. And a network access protocol. Kevin, can you read first, please?
Can you hear me?
Yes, I can.
All right. Sorry, I'm having problems with my stomach.
Understood. If you need to pass, we can move on.
No, I'm all right. Data link management protocols take the packets from IP and format them to be transmitted over the media. The standards and protocols for the physical media govern how the signals are sent and how they are interpreted by the receiving clients.
Excellent. Thank you, Kevin. Get you feeling better soon. All right. Let's see here. Now, so we know that we utilize some of these protocols to communicate over the internet or over the networks and stuff like that. And we talk about it, breaking it down and all that fun stuff. But the main thing is how do we know how to get where we need to go? Like I could say, yeah, I want this to go to DW, but how do I get there? In essence, I need an address, much like if I was sending somebody a physical letter, right? I would need an address to get to their house. This is where internet protocol addresses come into play. There's several pieces to it, although some of the biggest ones are made a little bit easier to understand based upon the binary work we did on Thursday and the hexadecimal work. We won't get as much into the hexadecimal stuff. Most of it will be in the binary arena, but we want to talk about the subnet mask. It's a way for us to kind of break networks down into smaller chunks. We're going to talk about our classes, public versus private addresses. Why do we do that? Ipi addresses. And then we're going to get into some IP version 6 as well. So the IP address itself is kind of a unique way to identify your computer or network device from any other, so it knows how to get to you. All these numbers are assigned by an organization called IANA, or IANA, the Internet Assigned Numbers Authority, and they're responsible for keeping track of all the IP addresses, who has them, what they're associated with, all that kind of fun stuff. Now, with an IP address from the IP version 4, which is what you're used to seeing typically, it looks like this right here. 4 sets of numbers broken up by periods or decimal points. And any of those numbers can be from 0 to 255. There's about 4 billion of these addresses total. That's 4 billion possibilities based upon these sets of numbers. Sounds like a lot, right? Well, back in the mid-90s, we started to realize real quick, we were running out of addresses, like really fast. I think towards the end of the 90s, we ran out of IP addresses. So they started working on other protocols to kind of take over for this. But in the meantime, we had to do a little bit of tech magic to kind of buy us some time. So we started utilizing things called public and private addresses. Things that could be used inside networks, but not routed over the wider internet, and then addresses that are routed over the wide internet in themselves. And then also, we had to break them down into classes so that when we're handing IP addresses out to people, we can hand them out in chunks based upon the sizes of their networks. And that's where that's where subnetting comes into play. We'll talk a lot more about that in just a minute, and then we'll have a workshop on subnetting tomorrow afternoon. So since we know we're running out of addresses, and even with the the network translations we use, still running out of addresses quickly, especially when you start taking into account the Internet of Things, where every toaster, washing machine, oven, doorknob, everything has to have its own network address, right? So each one of these things have to have their own IP address. So there's no way we could function with an IP version 4. So IP version 6 came about and tries to solve this problem. Other than, or excuse me, as opposed to IP version 4, they use a hexadecimal based system for their IP addresses. And with the way that they have them set up, the number of possibilities you have for hexadecimals is 320 undecillion addresses. That's 320 with 32 zeros behind it. To kind of give you an idea, that's more addresses than there are grains of sand on the earth. So that will last us for quite some time, right? So, but not everybody has implemented the IP version 6 yet. Networks are starting to adopt it. It's the the transfer is happening pretty quickly now, but still many internal networks and some older networks still operate off the IP version 4 frameworks. Questions so far? Said IP version 4, roughly 4 billion. Greatly magnified when you start getting into the IP version 6. All right, so let's talk a little bit about the subnet mask. So your IP address can look something like this. So this would be what a standard IP address would look like. Now, within this address, it's actually composed of 2 different types of addresses combined. You have the host address, which is the address for your computer, and then you have the network address, which identifies what network that host is operating on. The subnet mask determines which bits refer to the network address and which bits refer to the host address. So the bits, when they come across, what it'll be is it'll look something like this. So when we do subnet mask in binary, so this is what the subnet mask will look like when your computer sends it over the internet. So you'll have a series of 1s followed by a series of 0s. Series of 1s tells the computer, the receiving computer, or the routers, which part of this information is network. So the 1s are the network, the 0s are the host. So if I was looking at this address over here, the 192.168.15 would be my network address, because that's that first 3 groups, right? And then the last set of 0s would be my host. So my host on that network would just be 20, identifying my computer. As Oscar's putting it in chat, we'll look at it that way too, which is the so it would look this way. So remember, if we turn on all 8 bits together, we get 255. Do you remember that? So that's how it's represented down here. So 255.255.255.0. This is the same thing written out in binary. And what this is basically saying is the first 3 groups of numbers in this address are my network. That last chunk, that 0, that is my host. The easiest way to think of this is kind of like a city versus a street address. So the network would be the city you live in, and the host would be your address in that city. Right? So first we need to tell it what city to go to or network, and then what address in that city we need to talk to. Questions so far? All right. So here's breaking it down, kind of showing you what I was talking about. So we have the series of 1s followed by a series of 0s. When we write that out, it's like 255.255.255.0. Over here, we can see that same thing, 255.255.255.0. That would be a Class C address. Now, your Class A's, those are your huge networks. Those are like giant companies, like Google itself would be a Class A network. So it's giant organizations. I think you have something along the lines of like 10 million addresses or something like that within a Class A network. So it's a lot. When you get down to a Class C, we only have that last little octet right there to be a host address. So you can have a maximum of, was it 254 addresses on a Class C. So think of it like, you know, cities. Now your Class A's, there aren't that many of them. So that would be, they have 126 total Class A networks, not that many. So think of it like giant metropolitan areas. There aren't that many, right? You have like in the US, you have like New York, Chicago, Atlanta, LA, Miami. It's not a whole bunch of them, but in each one of those, they have a ton of people, right? So we're gonna have to have a lot of addresses in those networks to be able to communicate with those people in those giant cities. Now, we get down to Class C networks, there's a whole bunch of Class C networks. Several million Class C networks available, much like small towns, right? So you think about how many major metropolitan areas you have versus how many small towns. You have a whole bunch more small towns, but there's not that many people in each one. So we have a whole bunch of small networks with only like 255 or less in those networks. So that's your Class A, Class B, Class C. Class B is middle of the road. That would be like your universities, decent sized companies, stuff like that. Class C's would be small companies, homes, things like that. So Class A, giant organizations like Google. B, mid-sized companies, slightly larger companies. Class C, very small companies and homes. Questions on A, B, and C? Now, yes, Kevin.
I'm a little bit confused by this chart, because it says like the value in the first octet is like 1 to 126.
Yes.
But over in the next section, it says that there's 255.
Yeah, I could have been slightly off on the numbers. I apologize. Yeah, there's 126 networks right here.
Okay. All right.
So you can
not the next slide. I meant like.
Oh, right here.
Oh,
okay.
yeah.
So when you turn on all of your This is where we get into what breaks down these networks. So a class A network is also the value of a single bit. So when we go to our ANDing, we remember this one right here. Okay. So let me put this out here. So basically the first bit in this would be considered the network. So if I turn all of these on, I get 127, right?
Okay.
And you may be thinking, why don't we have 127? We only have 126, right? Because 127 specifically is a unique address. Remember when we talked about the loopback plug, which is that little physical piece of hardware that you plug in and it cycles the NIC and makes the lights come on to make sure, so you can test and verify that the NIC actually works. Do you remember that?
Mhm. Yep.
This, remember how I said there was a software way to do that? The 127 address is that software way. It's called the loopback address. So we come back to here. So what it is if I turn all that on, I could get from 0 all the way up to 127 without turning that bit on, right?
Yep.
Because once I turn the bit on, it's 128, as we can see right here, correct?
Okay.
So that's where they're getting those numbers from. So it's going from 0 to 126. 127 is a unique address. So any address where the first octet, like this first group, if it's anything between 0 or 1 and 126, that is a class A address.
Okay.
If any of you have Comcast, many of your IP addresses start with 10. That's a class A. Comcast is a class A network. So anything 0 to 126 equals class A.
So a class A wouldn't have 255 as its first octet.
No, that's the subnet mask. That's telling us that only the first octet, or that first group of numbers right here, is our network address.
Okay. Alrighty.
Because remember, we would still use some of these numbers for class B, C, D networks as well. But they isolate 1 to 126 as strictly being your class A networks.
Okay.
Next, for a class B, we would turn this one on. And we would have 128 would be the start, because this one's on, that eliminates the class A's, right? We could have this one on all the way up to another bit. So 128 to 191 is a class B address, because everything up to turning that second bit on. We come back here, 128 to 191.
All right.
Making a little bit of sense.
Yeah. Yeah. It's just it's a little.
It's the first time you're seeing it, so I'm not expecting it to make complete sense.
Some of it makes sense. Some of it like doesn't. You know, like.
Okay. But understand, I mean, you don't necessarily need to memorize all the fun stuff with the binary, but just understand that that's where the numbers are coming from. When I was coming through the cohort, I thought it was completely arbitrary. It made no sense to me whatsoever. I just thought I had to brute memorize it. I thought they just pulled these numbers out of thin air, and that's what it was.
Okay.
But they actually come from somewhere.
All right.
Can I suggest something?
Yes.
Oh, okay. I think for Kevin and like just because I remember back when I learned about this, it made a lot of sense when I put it over. All right, so if you put actual IP address, just any IP address above it, and kind of like break down which one we're paying attention to. Like so, in the to the right of your screen where you have the 255, 255, 250, if you just type another address, yeah, like put it real close to it, Yeah, okay, when you're done. And then drag it on top of it now, and then just basically break down what is it that we're paying attention to. It kind of helps identify why, you know, it's like
Yeah.
that.
So,
So the mask and the address are two different things.
Yes, that's what I want you to.
Oh,
yes,
okay.
what
yes.
it sees is
that's
the mask. The mask is telling me this 255.255.255 is telling me that the first 3 chunks of the IP belong to the network. That's identifying that network.
Okay, and so all right.
And then this 0 will tell us what is the host, and then down here would be the host.
All right, that makes a lot more sense, because I was like, wait, but if it's 255, it obviously can't go. That's way over 120. I was like,
Yeah.
But the mask and the all right.
The mask,
Yeah,
see what the mask does, the mask comes first, and it's telling the router or whatever what part of the IP address is associated with network and what part of the IP address is associated with the host.
And so then when the IP address comes through, it reads it as like, all right, okay.
So then it'll read those first 3 chunks and say, okay, it goes to this network. And then when it gets to the network goes, okay, last chunk, okay, it goes to that computer.
Alrighty, that makes that cleared that all up for me.
Cool.
Thank you.
Okay, and then the subnet mask can be notated in 2 different ways. One is like this, where it says 255.0.0.0. That is class A.
Yeah.
Or it can be at the end of the address and be like a /8.
Yeah, see, and
class A.
this slide makes that make a lot more sense than when they explained it in Coursera.
Yeah, because it's the first 8 bits that determine it, right? For a class A. So it's this first 8 bits. That's why they put a /8.
Yeah, that made it a lot more.
And then for a B, it's the first 2 octets or 2 groups. So it's 16 bits, right? So it'd be a /16. So /16 means a class B address. And then so forth to a class C, where it's the first 3. Granted, I know this isn't a class C address. We're just using it for an example. But yes.
Alrighty, thank you very much.
No problem. These numbers, at least for A, B, and C, you need to know off the top of your head. So 1 to 126, if you see an address in that range, you should know off the top of your head that is a class A. 128 to 191, class B. 192 to 223, class C. Those 3 you should know. So I'm saying, please make note cards for this. When you see those in the first octet, which is this first set of numbers right here, when you see these numbers in there, it should instantly tell you what class of address you're dealing with.
Alrighty, thank you, and thank you, Greg, for helping out with that, because that was really the whole thing on the side was what really made it click. So
Yeah. I remember, man. I remember like it was yesterday, man. So yeah, I remember how difficult it was first time.
Yeah, it was never explained to me. Like, it was just basically just know this. And so like, it didn't make sense to me, because I need to know why for something to make sense to me. Just saying
that's exactly what it was. Like, I was like, wait, I don't know why.
Yeah, because if they just say here, it just is what it is, memorize it. It doesn't make sense to me.
Yeah, exactly.
So
yeah, and it gets more complicated from there, just like, you know, man.
Yeah,
there's more to it, but
wait till tomorrow afternoon.
Oh, are you doing it? You're not doing those funky ones though.
Yeah, we are. We're going to do /25 and /27.
Oh, really?
Oh, yeah.
Okay, all right.
We'll be introducing that tomorrow.
Okay.
All right, so here it kind of breaks down the networks and lets you know how many networks we have. So we have 126 class A's, which are the really big ones, right? Because we can have 16 million hosts in each one. So again, go back to our city metaphor. There aren't that many really, really big cities. So there aren't that many really, really big networks. Same thing. So We have 126 networks. That network address tells us which big city to go to. And then our host address tells us which, what street address do we need to deliver the package to? Much like sending a letter. And then in the middle, we have 16,000 Class Bs with 65,000 hosts on each one. And then Class C, we have just about 2 million and only 254 hosts on each network. Good one to take a screenshot of just to kind of remember. And again, this is based off of the IP address. Questions, please, if you have them, please ask. But this is a good one to have a screenshot of, as well as the one before it. Does anybody need me to go back to the other one to get another screenshot? Nope. Okay. So within each of these groups, the majority of the assigned address is assigned by the IEEE or in IANA are meant to be used for public IP addresses. And these are usually received from your ISP. So like if you have Comcast or Verizon or what have you, they give you an IP address and a certain number of they may give you a certain number of IPs you can use. You may only get one public IP address. But the thing is you may have a multitude of private IPs working inside your network, all sharing that one public IP address. And all the classes like we were talking about, they are classed by their first octet. So as we talked about earlier, 1 to 126, Class A, 128 to 191, Class B, 192 to 223, Class C. And then when you start getting into D and E, D is for multicasting, and E is for research and testing purposes. See, Rebecca, can you please tell me how we would notate a Class A subnet? What would it look like?
Class A,
Yes, Class A.
the numbers start from 1 to 26 and 25.0.0.0.
255.0.0.0. Beautiful. So yes, that is how we would notate a Class A subnet mask. 255.0.0.0. Is there another way we could notate it?
What's the network?
No, like another way we /8, perfect.
Yeah.
So /8 would be another way we could do a Class A. Beautiful. So 255.0.0.0 or /8 after the IP address. And that would be a Class A address. Excellent. Thank you, Rebecca.
Yeah.
Private addresses. So as you kind of heard, when we're talking about, you have your public address right here, and then you have a private address, which is an address that is routed internally on your network only. Many of you, if you go and you do a IP address, like, you know, if you do an IP config /all, you would get a private address back as your IP. Because what's happening is in order to conserve addresses, you may have 50 devices in your house all working off the internet. So you may have a public address that might be 23.165.195. So you may have a public ID, address that's like this. But what's happening is you have your router. And then inside your network, you may have a bunch of computers in here. Each one has a different IP address. But say you have one that is so you have this address internally for this computer. So when you run an IP address or IP config on your computer, it tells you your address is 10.5.78.12. When you send communication out, it goes to your router. Your router takes that information, converts it so that when your router talks to the internet, the internet sees this address. That's how we conserve it, where you can have 50, 100, whatever computers behind a router, all sharing a single public IP address. It's how we conserve IPs. You know, because like at your house, you have your Ring doorbell, you have your smoke detectors, your washing machine, your dryers, your washers, your ovens. All of that stuff has its own little IP addresses, but they're all sharing a single one on your network on the outside. When your router does this, when it translates a private IP address on your internal network so that it can be routed over the internet on a public address, it does this through something called Network Address Translation, or NAT. This is the funky magic that was needed to preserve IPs over the network as a whole, so we didn't run out of IP addresses. We broke them up into public and private addresses. So yes, this is Network Address Translation, or NAT. And this is performed by your router.
So, so the internet never sees those private IP address. Like when it goes out into the internet, it only sees the public one.
Correct. In fact,
Okay.
You can't even route the private ones over the internet.
Okay. So your router is the only one that recognizes those private IP addresses as something.
Correct.
Okay.
And it allows a whole bunch of items to share a single address. So like a big company may only have 2 IP addresses. And then it shares, like all the computers in that company may share like 2 addresses or something like that are public facing. But internally, they may have 1,000 or 2,000 addresses in the computer or more than that. Does this make sense?
Yeah, no, it makes sense. It's just kind of mind blowing.
But that's how they've been preventing us from running out of IP addresses.
Yeah, I just never really knew how any of this aspect. I was pretty good with like hardware aspects, but like now that we're into this is the stuff that completely blows me away.
Gotcha. But it'll again, first exposure, it seems like a lot. The more you work with it, the more you deal with it, the more familiar it becomes. Again, we're not asking everybody to be experts right now. This is first exposure. Or if you're ahead on or if you're up on your readings, maybe second exposure. Now, so here's the address ranges for the private addresses. So a class A would be between 10.0.0.0 to 10.255.255.255. Remember I said if you had a Comcast, if you're a customer of Comcast, your address, if you run it, almost guaranteed falls in this range. There are two ranges for class B. So you have 172.16 all the way up to 172.31. And then you have 169.254. .0, excuse me, all the way up to 169.254.255. And then class C is the 192.168 range. This is one of the most common ones you'll see, 192.168. Do you need to know these ranges for private IP addresses? Yes, you do. So much like I said, you need to know the class A, B, and C's on site based off of that first octet. You do need to know these ranges and what they're associated with it. They're private addresses for A, B, and C. So absolutely need to know these. And there's some special IP addresses that you'll need to know as well. Yes, Kevin.
The ranges, like what's in between 10.0.0.0 and 10.255.255.255? Like what's in between that?
You could put in 10.1.15.37. You could put in 10.254.16.8. It's all those ranges that could go in between those two.
So okay, so it's any number in those 3 zeros, any number
Yes.
up to 255.
Correct.
Okay. All right.
Yeah. So okay, most companies that I've ever seen that have more than 100 employees, they're going to use a class A because they have VLANs. They have other locations. So they would use the first, the 10 to be the company. The second one they'd use as a location, and the third they'd use as a VLAN.
Yes.
So that's typically how they do it.
We haven't got into virtual.
We haven't done VLAN. Okay, never mind. What it is like a separation of like traffic types.
We're going to talk about VLANs probably tomorrow or the next day. We'll get into it, Kevin or Craig.
Gotcha. Sorry.
Oh, we don't want to add another complex. Thought on top of what we're already dealing with. But yeah, we will get into VLANs here in a little bit. So, does that answer your question, Kevin?
Yes, thank you.
All right, excellent. So within these, and on top of these, unfortunately, yes, Rebecca.
I didn't get the difference between the two class Bs. What is the difference between the two of them?
It would be any address that would fall between 172.16 and 172.31. So I could have 172.22.15.5 all the way up to like 172.31.18.7. As long as it falls in between these two addresses.
They're the same amount too, though. They're the same amount. It's a matter of choice. It's what you prefer. A lot of Wi-Fi networks use 172.
That is true.
Yeah,
Oh,
169. Not so.
And then, sorry, go ahead, Greg.
No, I was saying 169 is not so prevalent. That's all I was saying.
Yeah, 169. Yeah, no, because there isn't that many addresses available for it. So if it starts with 169.254, you have these last two octets to be your address. As long as it starts with these two numbers, the last two would be anything with those last 2 octets, as long as it falls in there, would be a class B.
So why wasn't just for the class B just be like between 169 to just like the 172? I'm kind of confused why there's like 2 different class B.
I'm not sure as to the history why they did this. I just know that they broke it up into these 2 groups.
Okay.
So, but if I'll look it up, and if it's relevant, I will bring it back up and let you know. But try not to overburden you with information as much as I can. All right, so special addresses we need to know about, especially for troubleshooting and things like that. One of the most important addresses you'll know is the 127.0.0.1, which is your loopback address. So in a troubleshooting sense, what we can do is we can do what's called a ping, which is sending out just some quick packets to an address to see if we can communicate with those devices. 127 would be sending a ping to your NIC, so your network interface card. So rather than plugging in that piece of hardware, we would just ping the loopback and it would send a signal to your NIC from your NIC. And as everything goes through, it'll say 4 packets sent, 4 packets received, everything okay, here's how long it took. So your loopback address is just testing the network interface card on your computer. So it's the loopback address. If you go look up the IP address of your computer and you see 0.0.0.0, it means you have not been assigned an address. So either one was not put in or what have you, but they do have a protocol that actually aids in this process. And then 255.255.255.255, which is all bits on all the way across the board. That is your broadcast address. It means you're basically speaking out to everybody in your broadcast domain, sending out whatever message you need to send, whether it be what's called an ARP request, you know, or something like that. You're basically like, hey, my name is Kelly, I'm here. Who else is on the network with me? Trying to get responses or what have you. Or hey, who's at this MAC address? And then the system will respond with an IP or with a MAC address. So that's what 255 all across the board is. That is a broadcast address. So whenever you see 255 in this last group here, that is a broadcast. It's sending it out to everybody on that network or that broadcast domain. Does that make sense? So whenever you see it in the last group, 255 is reserved for broadcasting. Another good one to have a screenshot of if you have not. Yes, Greg.
All right. Just responding to that, and anybody else that's kind of struggling with placing this or putting this into context. If you think about your phone number, it's pretty much the same. If you think about the first number, if you're from another country or you're from the United States, or you were familiar with how they do these numbers, you have a country code, right? In this case, it would be the company code. Like it would be, you know, the first number. So the 10 in the class A, that would be your country code. Then, you know, if you're from my city, 954-561 is our area code. That would be your area code in this sense, right? So you use the second number as your area code, and then most carriers get numbers in blocks. So if you have the first area code, then you have that second group of like 3 digits. Those 3 digits usually come in big chunks to a provider like T-Mobile and so forth, right? So those, I mean, originally before they started, you know, before you move to another carrier, they get them in blocks. So that would be what that company provides you when you first go to them to get service. And then the last digit is your unique identifier in that case. So it's kind of the same way, where it's like you move from the last number is the closest thing to you or you yourself and then you move further out until you get to a country. If that makes any sense at all, if it lines up for you, I hope it helps.
It's not an easy concept to grasp right off the bat.
Yeah. Oh, thanks. I appreciate that, Yuki.
All right. Do a quick little time to climb.
You want to pause?
Yeah, let me do that. Thank you. All right. Any questions? Based off of what you were seeing with the subnet masks, on the surface is kind of easy, right? The 255.0.0 is A, /8's an A. So you're able to kind of translate these things a little bit better. So like you guys did very well with that. Another address we need to be aware of, as it really helps with diagnostics, is APIPA, which is Automatic Private IP Addressing, APIPA. And it's kind of fun to say. Microsoft added this so that, remember what we said, if you didn't have an IP address, it was 0.0.0.0. Well, if you have that, you can't communicate with anything on the network. So what Microsoft did is they created a program that would give you an address like this. It cannot be routed over the internet, but it would allow you to communicate with other systems on your network in order to help diagnose what the problem you're experiencing. So instead of getting an IP address from our DHCP server, we would assign one to ourselves randomly, and it would start with 169.254. If you see those two numbers, anytime you're working on a computer, it means it cannot communicate with its DHCP server. And DHCP stands for Dynamic Host Communication or Configuration Protocol. And basically its main purpose is it hands out IP addresses to everybody on the network when they connect to it, so that they can talk to each other and out over the internet. But if it can't communicate with that, you have an APIPA address, and you can start diagnosing things, troubleshooting, and figuring out what's going on. Questions on this? So DHCP, or Dynamic Host Configuration Protocol, that is the name of the server that hands out IP addresses to everybody on the network. When you first plug your computer in and it talks to the network, it basically goes, hey, I need an IP address. And the DHCP server basically goes, here, I will lease you this one for 7 days. So they will loan you an IP address for a short period of time, allowing you to communicate with the networks and outside. Okay. A couple other terms we need to be aware of. One is Unicast. That would be if I wanted to communicate with DW directly, I could send, it's like sending a direct message. I'm communicating specifically with him and only with him, not with everybody else. So that is a unicast. From one single source to another single source. Then we have broadcast, which is kind of like what we're doing here. I'm broadcasting out to all of you. So I'm sending that message out to everybody, you know, on that network, essentially. That is what a broadcast does. So it'll target all devices on a single network. You can do a direct broadcast if you want to communicate with a remote network. So like if I wanted to communicate with Avery's class, I could send a message. That would be, you know, like me sending a message to another chat group or something like that, and it goes out to everybody in that group. But I'm doing this remotely. I'm not doing it in my network. If I hit 255 across the board, that is my network that I'm broadcasting to. If I want to talk to somebody else's network, I can put their network address in and then set the last one for 255. And then you have a multicast, which is from a single host to multiple destinations. So if I wanted to communicate with 5 of you, I would set up a communication, a multicast where I could communicate with just 5 of you on this group. So we just need to be kind of aware of these 3 terms, what they mean. Unicast, single sender, single receiver, broadcast, sending out that message to everybody who can hear. Multicast is from me to a specific group of people. Questions so far? All right. So that's all the IP version 4 stuff that you really need to know. Now we move on to IP version 6, which is the new upgraded model of this, of network addressing. So before, we had a 32-bit address, right? It was 4 groups of 8 broken up by decimals. So 4 octets, 4 groups of 8, 32 bits. So it's a 32-bit address. Now, when we get to hexadecimal, they have 128-bit addresses. And they use the hexadecimals like we talked about last Thursday. They use 32 hexadecimal characters, and it's divided into 8 groups divided by colons. So it's these double dots here. Now, since that is a lot to type out, like if you had to type out this many letters every single time, that'd be a lot, right? There's a way we can compress it or consolidate it. One of that ways is to eliminate leading zeros in a particular field. So if I have in a group, say I have (003F) in one of these groups here, this could just be rewritten as 3F. I eliminate the leading zeros. If I have (3F00), however, I cannot eliminate those zeros. They have to remain. Anything that is behind numbers or letters, any zeros, must remain. Only if there is nothing in front of them can we remove them. Because we know all the bits that lead up to that are just going to be 0, 0, 0, 0, 0, 0, 0, right? Now, the other thing we can do to compress is if we have, they say contiguous fields, but if you have a series of fields that are nothing but zeros, we can replace that with a double colon one time. So as you can see in this one right here, they have the FEDC, then a series of zeros. Then they have the 00CF, series of zeros, B8, 98, and then 1, 2, 3, 4. They can put the FEDC and then put the 2 colons, which represents this chunk right here with the double colon. So they condense this down to 2 double colons. We know whatever's in between there is nothing but zeros. And we know based upon how many fields we have, how many fields are in those double colons. And then you can see they eliminated the leading zeros here to give us CF. And then they eliminated the leading zeros here, even though it's 4 zeros, leaving us with a singular 0 right here. Does this make sense? We can do a little more practice with it. All right, so here's another IP version 6 address. What are some things we can do to make this a much shorter number?
For
See
the
here.
third, oh,
Go ahead, Melody.
I was gonna say for the third group and the fourth group, you can do the double colon.
So this group and this group, we can replace it with double colons. Okay.
The leading zeros of the fifth group can be condensed to just the number 6.
Make this number 6.
And I'm
then
guessing the last group, you can do the same thing.
and the
Okay.
group before that, you can take away that 0 too.
2. This becomes C52. So we're eliminating the leading zeros. Boom, boom. Almost everything with consolidation has to do with zeros, right?
Mm-hmm.
So any leading zeros, we can eliminate them and just end up with the last pieces. And then if we get a group of them, one time we can replace it with a double colon. So we can rewrite this.
An exercise like this would be on the test, right?
Yep.
Okay.
So we could rewrite this to be A7D 5 7 29 F colon to replace the 2 sets of zeros. Next would be 6, since we eliminated the zeros in the front. Colon. Why didn't we do anything with this one right here? Got a bunch of zeros in it.
Not leading.
They're not leading,
Mean
so they
something.
got the character ahead of them.
Mhm.
So G colon. Then we eliminate the 0 here, leaving us with C52. Another colon, and then we eliminate the 3 zeros in front of the 2, making it 2. So we've taken all of this and consolidated it down to this. Is that making more sense?
A lot of sense. That one down there, when you explained that one, because I actually did not know that you could condense 3 sets of zeros down to 2 colons.
You can
That
do it
was very
4 or
important to me.
5, you know, as long as it's a
Yeah.
group of zeros, you can always bring it down to 2 colons.
That's crazy.
It doesn't
Yeah,
matter
I
how
didn't
many
know that
sets,
part.
but you can only do it one time.
Yeah.
Do we know
Can you do
why?
an example? Can you do an example with, like, let's just do, say, for example, that FEDC down there. Can we do where that CF is still all zeros? I want to see what that would look like, because that's crazy for us to figure out that it will be all zeros in between.
So,
Can I
what it
give
is,
you
you know,
one?
there's 8 groups. So 1, 2,
Yeah.
3, 4, 5, 6, 7, 8, right? Here we have 1 unknown, 2, 3, 4, 5. So we have 3 missing. So we know 3 sets are in here.
Is
make
there
sense?
a reason why we can only do the double colons once, or is that just?
I love
You
that
wouldn't
question.
know. Yeah, you
I
wouldn't
love
know. I
that
mean,
question.
the
Let's
other
do
one.
an example and we'll show you why.
Yeah, the math would make sense. I see what you're saying, though. It makes sense.
So
Can I give you one?
kind
Can I
of
just give
use-
it to you? Can I give
Huh?
you one so that can I give it to you so that it make it more complicated for us to look at it?
Well, let's
like-
deal specifically with Melody's question and then we'll do another
Oh,
one.
okay. It is Melody's
So-
question, but I'm not sure.
Yeah, so here we go. FEDC colon 1, 2, 3, 4 colon 1, 2, 3, 4 colon 1, 2, 3, 4 colon. OOCF. Then 1, 2, 3, 4. And then 4. Okay. So say you have an IP address like this.
There you go. That's exactly what I was going to give you. There you go.
So you have 3 sets, 3 groups of zeros, and you have 2 groups of zeros, right? So let's say we consolidate that down to EDC colon colon CF colon colon. So say we consolidate it down to that. So looking at our address, you know, we have 8 groups. So 1, 2, 3, 4, 5, 6, 7, 8. We come down here, we only have 1, 2, 3. So we have 5 missing, right? Which set do I put the 3 in? Which set do I put the 2 in? Does that make sense? So how we would actually notate it, because if we do it twice, we don't know how many groups go in which section. So if I do it this way, if I have the FEDC colon colon CF colon 0 colon 0 colon. So it would look like this. So we would know we have 1, 2, 3, 4, 5. We have 3 missing. So 3 would be in here. So we have 3 groups of 0. But even with that, we're removing the leading zeros there, leaving 1 behind. So we know that the leading zeros have been eliminated.
And you can do it the other way around as well, like keep the first 3 sets of zeros and condense the second, even though it won't be the most cute, I guess.
No, because they want you to use it, because since we're only using it once, we want to use it only for the one with the most. Or if you have 2 sets, like if there was like 2 sets of zeros and then 2 sets of zeros, you do it with the first one. And then for some reason, if there's only 1 set of zeros, so like if they only had a single set of zeros, we wouldn't do double colons, we would just do a 0. If there's only 1 set of zeros, all zeros in the whole thing. So if there was 7 with letters and characters, all right, I'm going to type out an IP address real quick. And then I'm going to ask you if it is a valid IP address or not. And you tell me why. If it is not a valid IP address, tell me why. Hold up, Oscar. Okay. Okay, so people are filing in. That's it. Why is it invalid?
It's because G is not part of hexadecimal.
Absolutely. Letter G is not part of hexadecimal. Expect a question like that with regards to either a MAC address or an IP version 6 address. Anything over F, so it's G, H, I, J, K, any other letters above F, invalid. Excellent work, Mitchell. Do we know where this is coming from? Does this make sense? Okay. Are we clear on consolidating IP version 6 addresses? Does that make sense now? Yep. All right, I gotta pause the recording real quick. I'm sorry, I got somebody at my door. So the last thing on this page would be our loopback address for the IP version 6, which is basically :1, which basically means everything is a 0. And then the last digit is just a 1. And that's our loopback for an IPv6. Easier to remember than the 127.0.0.1, right? You just have to remember :1. Types of IPv6 addresses. This one's a good one to kind of take a picture of because you'll likely receive a question about this. So you have the Unicast, which is very similar. It's a single address to a single address, but there are 3 types of Unicast. So you have the ones that can be routed on the internet, which is global Unicast, and they must begin with the prefix 2000. So your first group of your global unique address would start with 2000. And then you have the link local or local address, which means you can communicate with nodes on that same link. And those begin with FE80. So that would be your local network communicating with them. And then you may have a unique local address or ULA, which identifies a specific site within a large organization. Like if we have an office here in Jacksonville, an office in Atlanta, an office in Brooklyn. We want to identify the Brooklyn office separate from the others. We could use a unique local address or ULA to identify that specific office within a large organization. And then we have our multicast, which is packets are delivered to all nodes on a particular network. They don't actually have a broadcast for IP version 6. And you have an Anycast, which is used by routers, and it identifies the multiple destinations. They would deliver the packets to the closest one. So if I was trying to get to Brooklyn and I had offices or routers in Atlanta, Savannah, and Memphis, the closest one to me to get to the Brooklyn node would be Savannah, so it would jump from me to Savannah. And then I'll probably move up to Charlotte and then Brooklyn. All right. Do you want to take a quick 5-minute break? Kind of get up, get your blood flowing a little bit. So come back at 11:45. I'm going to pause the recording. So IP addresses get us where we need to go. How do we get them? Well, as an IT professional, you can set up systems to obtain IP addresses in 2 ways. That is either dynamic or static IP addressing. First one, which is the easiest, it's not the easiest, but there's static IP addressing, and that is where we would go in and we would manually enter in the IP, the gateway, and the subnet mask into our system, so our system knows how to communicate with the network. I say easier because it's, you don't have to configure anything else. You can quite literally just put it in there. Problem comes when you have thousands of IP addresses in a company. You have to keep track of all those IP addresses, who they belong to, and all that kind of fun stuff. That's a lot of work and a lot of stuff to keep track of. So we would actually use something called a Dhcp server, which would allow us to dynamically assign IP addresses. And so the Dhcp, as we talked about earlier, stands for Dynamic Host Configuration Protocol. And this is essentially a server that assigns IP addresses automatically from a pool of addresses that you have. So you can sit there and say from address, A all the way down to address Z. If somebody connects from our network, you would assign them one of these addresses. They also may call this the scope or range of IPs. that the DHCP can assign. If it fails to give an address to a host, then the host generates its own called the Ipi, as we learned in the previous slide, the Ipi address. Where is it? Here. So anything starting with 169.254, Ipi, automatic private IP addressing. When it can't communicate with its, too far, DHCP server, it gets an Ipi so that it can communicate with the outside world. Now, even with dynamic addressing, there may be some addresses that will never change that we will statically assign. Things that we always want to know where they are, like the gateway router, right? So we know how to get out of the internet. We don't want to have to find that every time, right? So we need to know exactly where that is. So that address should not change. Servers, especially if we use Pixie servers for remote desktops or virtual desktops, we would want to be able to put it into the BIOS and know every time it's going to that correct server, right? We don't want to have to redo this every month or so. The other thing would be printers. You want to make sure you're printing to the one closest to you and not, one in Ohio. Actually, I had that happen in my old company. My boss went up to Ohio for a conference, came back down, was trying to print out a manual for something. It was like 200 something pages, and he printed it like 12 times. And finally, somebody from Ohio called down to us screaming, "Please stop printing, please stop printing," because he had been tying up their printers all morning trying to print these manuals. And he was communicating with their network printer because he was up there for a week rather than ours. So, automatically. Now, if you want to see what your IP address is, you can go to the search function, click your start button, hit the little search prompt, type in CMD, and that'll bring up your command prompt. Once you go into your command prompt, you type in this fun little command here, ipconfig /all, and that will give you all your network information for your computer. It'll give you your subnet mask, it'll give you your IP address, it'll give you your gateway router, it'll give you your DNS server. All that stuff will be in there for you. Questions so far? Good command line to remember right here. ipconfig /all. DHCP is obviously the most robust solution. It requires the least amount of maintenance from our point of view as an IT professional. If we did static for everything, a huge chunk of our time would be caught up in just assigning IP addresses, documenting, keep tracking of where all this stuff goes. It can be a major hassle. Now, inside of Windows, we can go in and we can opt to automatically receive one or statically apply one. If you want to statically apply one, we need certain pieces of information. We need to know the IP address we're going to use. We need to know the subnet mask of the network we're working on. We need to know the default gateway, which is our router to get out. And we need to know our DNS server, which is how we translate web addresses into IP addresses. But we'll talk about that in a little bit. So these 4 pieces of information would be the key ones we need if ever we're putting stuff in manually. So how would we get there? we would go to our network configurations, right click, go to properties. Once we're in here, so here's our properties. We would go down to our IP version 4, click on that, go to properties again, and that will take us to our IP address. Please take a screenshot of this, practice going there on your computer or in test out labs. They do have a few labs where they deal with reconfiguring your IP addresses. So this is a really good one to have good muscle memory on getting into and reconfiguring. Questions so far? All right, so gateway, talked about that here briefly. That is the router on the edge of your network that allows traffic beyond your internal network. So it's how you would communicate with the outside. That is your gateway. That's basically what that means. And we talked about earlier where it takes those private IP addresses and then changes it over to a public IP address so it can route over the internet. And that is the network address translation. So we talked about that one a little bit earlier as well. Questions, comments, concerns? Nope. All right. So we briefly talked about this earlier, an FQDN, or fully qualified domain name. So if we were going to go talk to Google, it would be www.google.com. And that would be the fully qualified domain name for the Google search engine. And it identifies computer and network to which it belongs. But how it's actually getting there is via an IP address. So that same address that we showed before correlates with a fully qualified domain name as well. Now, how does it translate between the two? We use something called a DNS server, which is a domain name server, and basically it's just a giant phone book. So it takes the FQDN, or that fully qualified domain name. When you type it in, it sends it to the server. The server goes, yep, I know that address. It's linked to this IP address. I will send you on your way. Easy way to think about it. We carry essentially something like this with us all the time. Our phones. They're essentially a DNS server for us. We don't remember the phone numbers of everybody that we talk to, right? We just say, hey, call Oscar. Hey, call Bernard. And then the phone correlates that name with the phone number and then calls that phone number. That's essentially what a DNS server does. It takes the name of the web address you type in, translates it to the IP address. Does that make sense? All right. So all the DNS does is translate from a web address to an IP address so that the system can communicate. Oh, Man, do we need a review of this, or we good on this? Binary. Oscar's signaling he wants to do like 5 or 6 more. Give me a thumbs up. Are we good on binary for the most part? We don't need to be experts on it, but does it make sense to us? And then remind me later today, I'm going to give you access to the ANDing spreadsheet. That's the spreadsheet where I was doing all the binary and stuff on. I'll give you access to that. So you can play around with it and work on it a little bit, stuff like that. So, we went over this on Thursday. Should be pretty well ingrained in our memories, if not our nightmares. And, should make complete sense. I have another video that I'll share with you guys that kind of breaks down IP version 6 versus IP version 4, done by a guy named PowerCert. It's a really good breakdown. We'll watch it kind of at the end of this. And we have video games for those who want practice. I keep recommending it. Nobody does it. For those who want an idea for a Twitch channel, Flippy Bit. Basically, it's your bottom 8 keys. It's like ZXCV for one hand, BNM and apostrophe for the other. And with that, you create the binary, but they do it kind of like Galaga. You can kind of see it right here. Where you do the bits based off of the numbers on the aliens. So you see like BA. So you have to make B, then A. Fire missile. 4-2. Fire missile. This is all based off of the binaries you're creating down here. So it's practice. Make it at least a little entertaining to learn hexadecimal binary. So it's a little fun, something you can do. For those of you who want to feel a little bit worse about it, here's a 2-year-old doing Flippy Bit. So got a 2-year-old translating from hexadecimal binary, just for practice, just for fun.
I was gonna say I don't get it, but then you said there's a 2-year-old doing it, and I was like, wait a minute, I'm not gonna say
she's
that.
2 years old. So playing the game, I'm just kidding. The little girl actually was not playing it, but it is at least an entertaining game to kind of give you a little bit of practice with hexadecimals. If you want to click on it, I think this link on the, if you click the link, will take you there. It's at least kind of a fun way to practice with hexadecimal. My old mentor used to have a standing bet. If anybody could beat him in a Flippy Bit, he'd pay him $100. But he's actually kind of close to the all-time high score. So just a little fun way, get away from the practice a little bit. So getting into protocols here a little bit. So protocols are generally broken up into 2 camps. You have TCP, which is transmission control protocol, and then you have UDP, which is user datagram protocol. So most of the ports you'll use or protocols you'll use fall into one of these 2 groups. TCP is connection oriented. Both the sender and receiver are communicating with each other. They do the 3-way handshake so that they begin communication, and then they check to verify all data has been received and resends it if not. Typically web browsers, email, stuff like that, where you need to make sure all the data is accurate and correct, uses TCP. UDP is a connectionless protocol, otherwise known as best effort. Because when you're doing certain things like this, like streaming video or talking on a voice over IP phone or watching Netflix or the game or something like that, if you've ever had moments where the picture gets kind of pixelated, like it turns into little blocks, gets blurry for a minute, and then it just kind of continues on. So it happens, right? That's UDP in action. It's prioritizing getting the information to you as quickly and as best effort as you can. If you're watching a video and some of it pixelates, you don't want to stop and wait while it goes back and corrects some of those pixels that didn't get there the first time, right? Because that would just slow things down even further. That's why we call it best effort. So if you've ever been on a call and the call breaks up a little bit, it doesn't go back and correct those pieces that were missed. It just moves on and tries to correct the signal going forward. So it's best effort. It fires the information at you. It's not checking whether or not you receive it. It's not verifying whether or not you receive it. It's just a continuous stream of information, and you're trying to piece it together as best you can. That's UDP, or User Datagram Protocol. TCP, again, connection oriented, has that handshake where it's talking to each other, three-way, verifies the data is getting where it needs to go. It's where data integrity is important. Web servers, emails, things like that. You don't want an email via UDP. If it's missing pieces, it's not going to make much sense. You want it to go back and correct that information, right? So that's the difference between those two primary protocols. All right. Network sockets. It is software component used to connect to a LAN or a WAN, but can also be used to connect within the computer. These are kind of identified as ports. So it uses programming requests called APIs, or application programming interface. And it's one endpoint between two programs, essentially connected through a network. And these should not be confused with a physical socket. So when we're talking about software ports, we're talking about what protocols you're using. When we're talking about physical ports, we're talking about like your P2 connector, your DB15, your Ethernet, your USB. Those are physical ports. These are software ports, so they're a little different. Does this make sense? How it may be notated on a address here is, so see down here, they have the IP address right here, and then they'll do this double colon. And then they'll put the port number. Does anybody recognize this port?
SMTP.
SMTP. So you have your IP address, and then you put this colon, and then you're letting it know that you're connecting to SMTP port. Sorry to hear that, Kevin. And then here would be an example, like I want to communicate with a web browser. Here's the IP address. And then I would use this port, which is HTTP. All right. All right, some protocols and well-known ports. See if we can get a little bit of a break here. Stephen, can you please read for us?
Yeah, it says transmission control protocols, communication across TCP, IP-based networks take place using various protocols. Each of these protocols has a default port associated with it. Both the TCP and the UDP use port numbers to listen for and respond to requests for communication using various protocols. And there are a number of common protocols and their well-known port numbers that will be covered in the next slides.
Thank you. So when I'm communicating with the computer, the port number that I'm pinging them on, or I'm connecting to them with, lets them know basically what my business is. You know, why am I communicating with them? If I'm using an email port, obviously I'm there to communicate with email. If I'm connecting to an HTTP, I want to talk to their web server. If I'm communicating with an FTP, I'm trying to transfer files. So depending on the type of port I use is going to establish the type of connection I'm trying to make. Now, these are my sending ports, like the ports I'm trying to connect with. So the well-known ports, remember we mentioned early on, there are 65,000 ports on a computer, roughly. So you have your well-known, you have your ephemeral, and then your, there's a third one I'll try to remember here in a second. But there's, the ports are grouped into different settings. Common, well-known, and ephemeral, there you go. So these are the ports that we want to remember. Don't worry, we have a mnemonic to help with this. So first ones requires 2 ports, port 20 and 21. That is your FTP protocol, or file transfer protocol. That is a way to transfer files between 2 computers. You ever tried to send an email with a large file in it? It wouldn't send it because the file was too big. Way around that is to use something like an FTP protocol where you can send the file directly. So instead of trying to do it like some way over an email where they're going to have data restrictions or size restrictions, this would be another way to do that. Or if you forgot a file at your house and wanted to communicate with your home computer, you could go in through an FTP protocol and retrieve those files from your home computer. That's port 20 and 21. Next, secure shell, or SH. It is essentially used to pass login information to a remote computer and control that computer over a network with at least a base layer of security. So a secure shell. Next to that, we have Telnet, which allows you to control a computer remotely. Big caveat, this one is dangerous because anything you send over Telnet is sent in plain text. So if anybody's monitoring that line, they will see everything that is sent across that line. So there is no security over Telnet unless you apply other things to it. So Telnet, plain text, but it allows you to control a computer remotely. The one we're all familiar with, SMTP, or Simple Mail Transfer Protocol, we use to send mail to people. That is port number 25. The one we recently just talked about today, the DNS, or Domain Name System, it translates our web addresses into IPs, or FQDNs into IPs. That is port number 53. You are asking yourself, do I need to know these ports? You absolutely do. You are likely to receive several questions with regards to port numbers. Next group, we have HTTP, which is Hypertext Transfer Protocol. This is your web server protocols. There's a port 80. The next two are familiar to us, POP3 and IMAP. Those are our email protocols for receiving emails, and that is 110 and 143. Next, we have HTTPS, which is Hypertext Transfer Protocol Secure, which puts a layer of encryption or security over the web server transmission. If you notice when you are surfing the internet, you see that little padlock up in the corner. Sometimes that lock is open, sometimes that lock is closed. If the lock is open, that means you're operating over port 80, HTTP. It is not a secure connection. If the padlock is closed, it means you're operating over HTTPS, the secure protocol. Please don't ever send personally identifiable information when you do not have the padlock in place. Last two we need to really be aware of is RDP, or Remote Desktop Protocol. This is a Windows-based protocol that allows you to remote in and provide remote assistance to connect to another computer. That is 3389, Remote Desktop Protocol, or RDP. And then finally, we have AFP, or Apple Filing Protocol, obviously owned by Apple. And it is a resource sharing protocol, proprietary to them. These are the core protocols you need to know for the A+. They're a good start to get to know for the workplace. So like I said, we have a mnemonic that will help you remember these, and it puts them in ascending order. If you remember when I told you in the beginning, when I would come into class every day, there were certain things I would write down every single day to help me remember it. And one of the things I wrote down twice a day were my ports, until I knew them without having to think about them. Questions so far? All right. So some other ones we need to be aware of, at least as to what they do. We have our DHCP, which we talked about earlier. That's that network protocol that assigns IP addresses every time we connect to a system. We'll get a little bit more into some of these a little bit later. Our DNS, that's the protocol that translates fully qualified domain names into IP addresses, kind of like a phone book for the internet. And there are different ones. Most famous one being 8.8.8.8, and that is Google's DNS server. So if you ever want to check and see if your computer is able to talk to the outside network, internet, ping 8.8.8.8, and that server is never down. At least it went down, I think, recently, but typically never down. And it'll tell you if you're able to communicate with the outside web. SNMP, you will always see them throw that one in there as an answer when they're talking about email. They will have IMAP, POP, SMTP, and then they will throw in SNMP, which is Simple Network Management Protocol, but it's close enough to SMTP where people tend to get confused on it. And this allows you to manage devices on an IP network. So like if you're talking about like security devices, cameras, stuff like that, other routers, servers, you can use your SNMP to manage those devices. Simple network management protocol. Please do not get that confused with send mail to people. We have server message block, Microsoft protocol for reading and writing files and to requesting services from server programs. Oh, sorry, Ldap. Thank you, Oscar. Ldap, lightweight directory access protocol. It's kind of a protocol for accessing maintenance directories. It's kind of like a phone book for an organization. Like if you connect to it, it would basically say, here's where all of our resources are located. Here's where all of their addresses. That is the Ldap, lightweight directory is the key word in there. Directory access protocol. So it's kind of like a phone book for a network. Whereas the DNS is the phone book for the internet, Ldap would be your quick phone book for the network you're on. Then we have secure shell, which is pass login information to a remote network. Again, we talked about that previously. And then we had the FTP, which was file transfer, but there's no security on FTP. So anything you send, wide open. So they have a SFTP, which is a secure file transfer protocol, which allows you to encrypt those files as you are transferring them to make them unreadable. Questions so far on the protocols? All right. So remember before we had the DoD model, which was a 4-layer. Here is a look at the 7-layer OSI model right here. And it is labeled 1 up to 7. It has each of the protocols that operate on each of the layers. So you can kind of see where they come into play. And it gives you the name for each of them and how the information is put together. Oscar put in his one, which was like, please do not, please do not touch Steve's pet alligator or something like that?
Yeah.
Okay. The way I always remembered it was, please do not throw sausage pizza away. Whichever one you helps you remember it. And that is your physical data, network, transport, session, presentation, and application. The 5-layer Google model combines these 3 and just makes it an application layer. So you could just say, please do not throw away. So this is a 7-layer model. Typically, you would use this in networking. If you're trying to troubleshoot based on what's happening, you would know which layer to start your troubleshooting on based on the protocols that are malfunctioning. So not a bad one to get a screenshot of just for study purposes, although there is a graphic in the Cybex book, the big white book, that actually lines up 7-layer versus the 4-layer, so you can kind of see how they're connected. Public addresses, do we need to know these? We want to take a guess? No, we don't need to know these.
Yes. Oh, no.
No, I appreciate your enthusiasm, Golly, but no, we don't need to know this one. These are Class A addresses. So it's just a kind of.
I was just hoping that I was wrong.
You're hoping that you're wrong? All right. So VLAN, Greg mentioned this one earlier. We will talk about this one a little bit later because we've already gone over a lot of really big concepts. We don't want to add another one to it. So we will talk about that in a little bit. And it's kind of a way to break down your networks into smaller pieces utilizing switches. So we will talk about that one later on. Here's a nice little graphic for it. But again, later. We already talked about VPNs, which is a end-to-end encryption that allows you to communicate over the net. We talked about the regional locking of data, how that, you can go in the network here in Jacksonville and I can pop out anywhere. I can pop out as long as they have a server there. I can pop out in South Korea. I can pop out in Nigeria. I can pop out in Brazil, wherever. And I can have an IP address and be viewed by the wide network as being in that location. All right, here's the mnemonic. This puts all of the ports you need to know in ascending order. So smallest to biggest. For safe technicians, simple deeds help put immature hackers at rest. This was one of the things that I wrote down as my brain dump before I started my 1001. There it is. That way, when I was in the middle of the test, I didn't have to try to remember my port numbers and be kind of stressed out or rushed and not remember it in the moment. I did it all once real quick. And then as I went through, I could just quickly reference it if I needed to. Because they will allow you a whiteboard or something like that to take notes on during the quiz if you wish, or before you start, whatever. So this was one of the things I wrote down. And then what will happen is if like you're writing your ports down and you get to DNS and you can't remember, but SNTP is 25, HTTP is 80, the port number falls between those two, and it'll help you get it. So a good one to take a screenshot of. Yes, Kali.
You said they let you take notes before the test?
Meaning you're sitting down at the desk, you've started, and you can sit there and write stuff down if you wish. Not like you sitting in the waiting room with your notes, no.
Okay. So is that like, I don't know if you know where you took your test, but if you take your test at home, can you do the same thing?
They will have a whiteboard on the computer. You can't have one with you.
Oh, okay.
So there's one on the computer you can use. But what I did was I took 5 minutes and just did a brain dump. Like I wrote down my ports. I wrote down my 7 steps or my 6 troubleshooting steps. I wrote down my laser printing steps. I wrote down my 802.11 protocols. There was just a few things that I just wrote down before I even started the test. That way I'd have a quick reference to it as I was going through the test.
Okay.
But that was, something I did. I don't think Rachel or DW, you guys didn't do that, did you? Did you do brain dumps? No? Okay.
No, I didn't do that.
Gotcha. So it's kind of a personal preference thing, but it just allows you to create a quick reference tool for yourself while you're going through the test.
Gotcha. Thank you.
Mm-hmm. All right. Right on time. We should now be able, at least at a 10,000 foot level, explain the purposes and role of TCP in the internet and private networks. Explain the characteristics and properties of TCP IP, and explain common TCP and UDP ports, protocols, and their purpose. Any questions?